Welcome back to EET 260, and we're continuing with our riveting discussion of binary numbers system. In the second document, it's a 1 of 3, 2 of 3, and 3 of 3 situation. And here last time we talked about binary, decimal, and hexadecimal fixed point numbers. We talked about integers, and then we talked about how you could have a decimal point, and if you go to the right, things get smaller with the digits. In decimal it's 1/10, 100th, 1,000th, and so on. In binary it's 1/2, 1/4, 1/8, 1/16, and so on. And in hexadecimal it's 1/16, 1/256th, 1/4096. You can see that hexadecimal is even more efficient than decimal in the number of bits to represent a number. That's because it has 16 symbols per digit, as opposed to decimal's 10. And of course, binary requires a lot of digits or bits, if you will, to represent a number, because it only has 0 and 1. But again, as Claude Shannon gave us, 0-1 is great electronically because we can create very robust systems where we only have to discern one of two voltages to indicate a 0 or a 1, off or an on, a false or a true. And so that's why that's why these electronic control systems have succeeded so well with binary number system and binary digital logic. It may take a lot of numbers to a lot of binary bits to represent something, but those bits are easy to build, and once you've built one section, it's relatively easy to connect it to another section so that you can use a modular design technique. And again, there's just the two voltages, which makes it very noise immune, if you're not completely foolish. So now we got to look at this idea of negative and positive numbers. The first type of way of representing negative binary numbers is what they call the signed binary integers, or sign magnitude notation. In that case, what you actually have is, let me make this a little larger here. So starting, I guess we have 12 bits here. B10 down to B0 is 11 bits of magnitude, and in each case, the first two, these 11 bits on the right, give us the decimal value 425. But if we have a 0 in the sign bit, it's positive. If we have a 1 in the sign bit, it's negative. So the first one is plus 425, and the second one is minus 425. And that's all well and good, and although I'm sad to say, this notation is not very popular anymore. But if you ever run into something called sign magnitude notation, you'll know it's just a binary integer with a sign bit, and the 1 makes it negative. So it's that simple. A binary number with a 0 for positive in front, or a 1 for negative. And so this bit out here is really not part of the numerical value. It's just a sign indicator. There were, for a long time, there were some analog to digital converters and digital analog converters in the control industry that used sign magnitude notation, but that has diminished quite a bit. And most things nowadays, if they involve negative numbers, well, before I say that, sign magnitude, is pretty much gone. So let's look at 2's complement. Now this is an important fact right here, this sentence. In an n-bit binary number or word, whatever you want to call it, collection of n bits, one can create 2 to the n unique codes. And it'll be all zeros through all ones. It turns out that a fortuitous coding can be employed, and almost always is employed in every computer, microprocessor or microcontroller. The coding trick allows subtraction to be performed in the same digital logic unit as addition, saving logic and reducing the size of the chip. So, once again, not just for arithmetic, but for binary coding, this, I'll be asking this in homework and in quiz things. If you have n bits of binary code, you may represent up to 2 to the n things. So if you have 8 bits, from a number standpoint, you can represent 0, 0, 0, 0, 0, 0, 0, 0, 8 zeros, all the way up to 1, 1, 1, 1, 1, 1, 1, 1, 8 ones. All the zeros are equal to 0. And when you have 8 ones, it's equal to 255. So, that's 256 different codes, and 2 to the 8th, n would be 8 in that case, 2 to the 8th is 256. So that's a fact that's worth remembering. Now the way 2's complement numbers work, and we don't see this in decimal really, but it can actually be. There's actually such a thing as 9's complement and that sort of thing. I'm just going to shrink this down a little so it fits on one page. I guess I can make this a little bigger. There we go. Probably should do this like I get paid for it. And yeah, one too many. So here we have a 5-bit binary system. Now 2 to the 5 is 32. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So 2 to the 5th is 32. Now, the way this works, if you code the numbers in this fashion, 0 is 0, and here's our positive numbers. We go from 0 and we count up. 0, and there's a 1. If you add 1, this would be a 0, and it'll carry over. You'll get 0, 0, 0, 1, 0 right there. And then if you add 1 to that, you'll get 0, 0, 0, 1, 1. That's a 3. Add 1 to that, and it'll carry twice. It'll carry from this first digit over to the second digit, causing that to be a 0, and carrying to the third digit, causing that to be a 1, and that's a 4, and so on. And that's how the binary numbers count. So we'll go with a 5-bit 2's complement system. We'll go from 0 to 0 and 4 ones. Now 4 ones is a 1, a 4, a 1, a 2, a 4, and an 8. So 1 and 2 is 3, and 4 is 7, and 8 is 15. So it goes from 0 to 15. And you can see all the time we do that, the for 16 different codes, 0 through 15, we use up 4 bits. And all that time for those 16 codes, the bits are the most significant bit, or MSB, is a 0. If we want to go negative, you kind of wrap this code around from here up to here, and it becomes negative 16, negative 15, negative 14. And it counts in the same direction. You can see it goes from more negative toward less negative till it reaches 0 and goes to the maximum positive. So that is the 2's complement number system, and we're going to show you how to convert from positive to negative numbers in the 2's complement number system. To change a number from negative to positive or from positive to negative, invert all the bits and add 1. Now, inverting the bit means if it's a 0, make it a 1. If it's a 1, make it a 0. So let's change plus 11 base 10 to minus 11 base 10. Now, plus 11 base 10, we're going to need a 1 and a 2. That gives us 3. No 4s. And we need an 8. So 8 plus 2 plus 1 is 8 plus 3 is 11. So to convert that to minus 11, I invert 0, 1, 0, 1, 1 bitwise to get, okay, the zeros become 1s. And I, instead of 0, 1, 0, 1, 1, I get 1, 0, 1, 0, 0, to which I add 1 as follows. Well, here's my 1, 0, 1, 0, 0, and then I add 1, and there's no carries here. This one's actually easy to do, and I get 1, 0, 1, 0, 1. And that's negative 11. And if we look up on our chart here, negative 11 is indeed 1, 0, 1, 0, 1. If I add 6 base 10 to 7 base 10, I will get, now here's a 6. It has no 1s, it has a 2 and a 4. So it's equal to 0, 0, 1, 1, 0, and you can see that in this table up here. A 6 is 0, 0, 1, 1, 0. There it is, 0, 0, 1, 1, 0. And 7 from the table is just 6 plus 1, so it's a 1, 2, and a 4, that's 7. So I go to add them together. Well, a 1 and a 0 is a 1. A 1 and a 1 is a 0 with carrying 1, because 1 and 1 is 2, but we don't have 2 in binary, so we use 1, 0. So 1 plus 1 giving me 0, carry 1. 1 plus 1 plus 1 is 3, which is a 1. Carry a 1, and then 1 plus 0 plus 0 is 1, and 0 plus 0 is 0. Now, which according to our chart above, I add 6 plus 7, hopefully I'm going to get 13. I look at my chart above and I've got a 1, no 2s, and a 4, so that's a 5, and an 8. 8 and 5 is 13. And 13 is 0, 1, 1, 0, 1. Now, let's subtract 7 from 12. 7 base 10 from 12 base 10. So we cleverly remember that 12 minus 7 can also be written as 12 plus a negative 7, in which case we'll change 7 to a negative 7. So here's a 7, 0, 0, 1, 1, 1. So we invert bit by bit, and we get 1, 0, 0, 0, to which I will add 1 as follows. 1, 1, 0, 0, 0, plus a 1, and I get 1, 1, 0, 0, 1. And if you check that in our chart above, minus 7 is 1, 1, 0, 0, 1. Now, so instead of subtracting 12 minus 7, I just take the 7 and make it negative, and I add it to the 12. And let's see what we get. 0 plus 1 is a 1. 0 plus 0 is a 0. 1 plus 0 is a 1. 1 plus 1 is a 0, carry 1. And then 1 plus 0 plus 1 is a 0, carry a 1. But that carry 1 went out of our 5th digit, and we don't even care. Ignore the leftmost bit because we only have 5 bits. After which, according to our chart, you got 0, 0, 1, 0, 1. You can look at the chart, or you can just say this 1 equals a 1. I got no 2's, and I got 1, 4. Well, 4 plus 1 is 5. So now you can see how 2's complement numbers can be converted between positive and negative. And you can see that when you do addition or subtraction, you're always really adding. In the subtraction case, you're just negating the number in the 2's complement form and adding it. So it's they're both additions in essence, and that was a great savings. And this is the way almost all computers, microcontrollers, microprocessors do arithmetic nowadays, is in 2's complement. So that being the end of that, I want to also show you that as we go over to the Windows side of the world, and let me put that down. The Windows calculator has a mode that's really handy. So if I go down here and I type calc, and here, now the view right now is standard, right? And you've probably used scientific, and in scientific mode you can use the where is it there? I guess it's the, is it this exponent thing? I guess it's the exponent thing. So if I want to put 1 to the exponent of 4 and I hit equal sign, I get 10,000, right? So that's all well and good. And you can clear everything there. Now the other mode that's really handy in this thing is programmer mode. So yeah, okay, great. I guess they got a little memory thing there. What's nice about programmer mode is, you see how it right now it's set to decimal, because 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 are available. So right now it's set to decimal, and you can see there's a little blue tick right next to the word DEC right there. If I want to go to binary, put this in here, and I've only got 1 and 0. Now if I put in 0, 0, 1, 1, 1, okay, that's my number, and I hit equals. If I go to decimal, well, it already tells you up here, in decimal that's a 7, in hexadecimal it's 7, in octal it's a 7. And it makes sense, because I got 1, 1, 1, 2, and 1, 4. 1 plus 2 is 3, plus 4 is 7. And I guess this will, see this Q word here, you can cycle through. So here's a byte. So if I were to put in 1, 1, 1, 1, 1, 0, 0, 0. Notice it shows here in decimal as -8. So it actually does 2's complement. This is -8 and 2's complement. So let's clear all this. And let's subtract 2 numbers. Let's subtract 64 minus 41. So 64 is 164, 0 32s, there's 0 16s, 0 8s, 0 4s, 0 2s, and 0 1s. So there is a 64. Now we want to subtract 41. Well, 41 we would have if I were to do 41, let me bring up a notepad here. And let's make the font ridiculous, like 48, okay? So if I want 41 decimal, let's see, how do I convert that to binary? I could keep dividing by 2. Remember our algorithm, we divide by 2, and I could do that, you know, divide by 2, and that equals 20 with a remainder of 1. And then I take 20 decimal, and I divide by 2, and that equals 10 with a remainder of 0. And then I take 10 decimal, and I divide by 2, and I get 5 with a remainder of 0. And then I take 5 decimal, and I divide by 2, and I get 2 with a remainder of 1. And then I take 2 decimal, I divide by 2, and that's equal to 1. It's equal to 1 with a remainder of 0. And finally, I take 1 and I divide by 2, and I get 0 with a remainder of 1. And so our number has, let's see if we do it right here. We have 1, 2, 3, 4, 5, 6 bits. And of course I probably did it wrong. But 32, 16, 8, 4, 2, and 1. So it looks like we have a 32, and we have no 16s, and we have an 8. So 32 and 8 is 40. We have no 4s, no 2s, and a 1, so that's 41. So we come down here, and our number, so remember this guy here is our LSB, and this guy here is our MSB. And so our number, 41 decimal, is equal to 101001 binary. Now, that's great, but we wanted to subtract 41, so we got to find the 2's complement to this thing. And that's kind of why we're using 7 bits up here. So let's stick a 0 out in front of here. It doesn't hurt. Now we got a 7-bit number. Let's convert to 2's complement. So 0101001 becomes, first we have to do the 1's complement. It becomes 1010110. That's the 1's comp. Here, we'll cheat a little bit there and just stretch that out. That's our 1's complement. I wonder if we can actually fit that in. There's our 1's complement number. Now we have to add 1. So we have this number. Whoop. We have to add 1, 2, 3, 4, 5, 6. So we have to add a 1. Now, 0 plus 1, well, let's get all our numbers over here. 0 plus 1 is 1. 1 plus 0 is a 1. Yep, sorry. This next guy is a 1 plus a 0. That's going to have to be a 1. This guy is a 0 plus a 0. Here, see? 0 plus 0 is 0. I'll come back over here, and I got a 1. Now I've got a 1 plus a 0. That's going to be a 1. I've got a 0 plus a 0. That's going to be a 0. And I've got a 1 plus a 0. And that's going to be a 1. Okay? So this is our new number. This is equal to, so there's one's complement. Then what, whoops, sorry. And then what do? Add 1. And this is now equal to minus 41 decimal. So we have this. All right. So what I'm going to do here, and I'll be sure to post this little example. So in fact, let's put some more information on the top here. What are we doing? We're doing 64 decimal minus 41 decimal. So first, we're going to do just what did we just do? We just did what is 41 decimal in binary. That's what we did over here. And why don't we indent this so it looks a little better? Okay? And so 41 decimal equals that. Now we want to convert it to 2's complement. And I'm going to make this even wider here. At least I think I am. And so to convert this to 2's complement, we did two processes. We did the 1's complement, then we added 1. And there we got our number 1010111. Now, we're going to do 64 decimal plus a minus 41 decimal, and we'll do that in binary because we're trying to show how this binary 2's complement works. And what we have here is we're going to do this addition. So 64, as you remember, is 1 and 6 zeros. So I have 1, 2, 3, 4, 5, 6. And to that, we're going to add this guy right here. 1010111, because this guy is 64. Okay, 64 decimal, and this guy is minus 41 decimal. Of course, he's in 2's complement. We come over here like this, put our line there, and now let's perform this addition. Okay, and I'll have to do that kind of backspace thing. So I have a 0 plus a 1, that gives me a 1. I have another 0 plus a 1, that gives me a 1, and I have yet another 0 plus a 1, that gives me a 1. I have a 0 plus a 0, that gives me a 0. 0 plus a 1, that gives me a 1. 0 plus a 0 gives me a 0. Oops, sorry, gives me a 0. And a 1 plus a 1 gives me a 1, 0. But this 1, that's going to get knocked out because we only have 7 bits here. So our answer becomes, oops, sorry, 0, 0, 1, 0, 1, 1, 1. And that's our answer. Well, let's see what it is. This guy's equal to, let me do it this way. This guy is equal to 16. All right. This guy is equal to 8. This guy is equal to 4. This guy is equal to 2. And this guy is equal to 1. So what we have here is 16 plus no 8s plus a 4 plus a 2 plus a 1. And 64 minus 41. Well, 64 minus 40 would be 24. And you take away one more, it's 23. And here we go. I'm sorry, that was supposed to be a plus 1. That's equal to 23. And we can celebrate. And, as Michael Penn would say, that's a good place to stop. So I'll save this file and post it with this video. But you can see that you're able to do some calculations in here with this Windows calculator in programmer mode. Now if you want to go into hexadecimal, you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. All right. So there you go. So you should be able to try some of those things out, and do some simple binary arithmetic. Now we haven't done anything regarding how to do multiplications, but you can use the same addition algorithm that you use in decimal, where you do partial products and that sort of thing, or you can just do it in here. If I go back to binary and I clear everything out and I do 101, which is a 5, and I multiply it times 111, which we now know is 7, and I multiply it. Now it says decimal 35, with 5 times 7 is 35, but if we look at this, I've got a 32, I've got no 16s, no 8s, no 4s, a 2, and a 1. Well, 2 and 1 is 3, and 32 plus 3 is 35. So anyway, that's our look at binary arithmetic. We're going to look a little more at binary bit fields and see how we can use those in microcontrollers. But we'll see you next time, and have a good one, and best wishes.